Okay, welcome to part three, the final part of chapter 19. Um, and in this part, we're going to talk about some work done by a guy named Faraday who studied what we now call capacitors. So Faraday was looking at the fact that the electric field strength is proportional to the charge that's there, right? I mean, we saw this in with a single charge, E equals KQ over R squared, so it's proportional to Q. He also looked at the electric potential as proportional to voltage, right? So if E is proportional to Q and E is proportional to the voltage, then Q is proportional to the voltage, right? And that little symbol here, this little fish symbol here and there means proportional to. We call the proportionality constant the capacitance. Q equals CV, right? Where C is the capacitance, Q is the charge, V is the voltage. So we could solve for capacitance, and the capacitance is just Q over V, right? So from a unit perspective, is charge per unit voltage or coulombs per volt. Faraday named this unit the farad, or scientists named this unit the farad after Faraday. So we have 1 farad is 1 coulomb per volt. Well, if we look at a simple geometry of what we call a parallel plate capacitor, so we just got two square plates or two rectangular plates here. They've got a separation distance here, D. When we start looking at what the capacitance is, it turns out the capacitance is pretty easy to get. Capacitance of a parallel plate capacitor like this is epsilon naught A over D, right? A is the area of one plate, right? And the plates are the same, so the area of one is the area of the other. D is the distance between them. Epsilon naught is this quantity we call the permittivity of free space. And the cool thing here, epsilon naught is a more fundamental quantity than K. We have this number K that we've been using is 8.99, right, times 10 to the ninth newtons meter squared per coulomb squared. Well, it turns out K is equal to 1 over 4 pi. It's a bad pi. Epsilon naught, right? The more fundamental quantity is epsilon naught, and Farad was the first one to sort out epsilon naught, and it's called the permittivity of free space. If we put what's called a dielectric in the middle. Now, dielectric would be something like the top of your table in class. That's a good dielectric. Or rubber, or plastics. There are tons of things that are really good dielectrics that we use as insulators all the time. Glass is a good dielectric, right? If a dielectric fills the space between the plates, then the capacitance is kappa. That's that right there, that funny looking K is a Greek kappa. All right? You'll know this from fraternities and stuff like that, but that's a Greek kappa. All right, so capacitance is kappa epsilon naught A over D, where kappa is what we call the dielectric constant. And dielectric constant is just a number you have to measure for different materials. So the dielectric constant for air is 0. Is 1, pardon me, is 1. Um, the dielectric constant for vacuum, well, air, not quite 1, and a little bit of difference. Dielectric constant for vacuum is 1. Um, and you can see the breakdown voltage here. Our breakdown electric field strength, 3 times 10 to the 6 volts per meter. And then there are other fused quartz, right? Dielectric constant 3.78. Nylon, right? Nylon 3.4. Silicon oil 2.5. Strontium titanate 233. Teflon 2.1. Water is a dielectric, right? So what makes a dielectric different from other materials? Well, or from conductors. That's really a big one. Dielectric differs from conductor in one major way. The electrons in a dielectric are not free to roam, right? So when you put them between the charged plates, what you end up with an excess negative charge on this surface where the plus charge is, and you end up with an excess positive charge on this surface where the minus charge is. But none of these charges are free to leave the material. They're stuck to it. They're not going to be coming off until you hit the breakdown voltage or breakdown strength, right? Um, and this is why it increases the amount of charge we can put on the plates, right? If kappa goes up, the total charge we can put on the plates at a given voltage goes up. The reason for that is the dielectric in the middle orient itself to kind of in some ways cancel out some of the charge on the plate, right? You can think of it in terms of electric field lines as once this happens, some of the electric field lines penetrate all the way through, and some of them terminate at the surface where there's excess charge. If we look at the energy in a capacitor, or the voltage in a capacitor, let's say we got 3 capacitors like this, right? We know the voltage is Q over, and we're trying to figure out what the total capacitance of 3 of them, if we stuck them together like this, would be, right? We've got 3 of them, we're adding them together by putting one right after the other. What happens to total capacitance? Well, if we look at this, we got a voltage across this one, V1, plus a voltage across this one, V2, plus a voltage across this one, V3. So V1 plus V2 plus V3. Well, this is a conductor in the middle. The charge minus Q and the charge plus Q are all the same. All the charges end up being the same, or opposites to each other, and plus minus, plus minus, plus minus, right? Because of that, we look at this voltage, it's this plus this plus this. So if you pull out the Q, um, what's left is 1 over C1 plus 1 over C2 plus 1 over C3. That's the effective capacitance of capacitors in series. So capacitors in series, when you go to add them, add inversely, right? So you're going to add the inverse of all of this to get the capacitance. When we do them in parallel, it's not the charge that's the same on every one, it's the voltage that's the same on every one, right? So we got a Q equals whatever the parallel plate, the parallel capacitor capacitance is, times the voltage. And that gives us Q1 plus Q2 plus Q3, which is the total voltage, total charge, right? Which is C1V plus C2V plus C3V. Okay, that's great. So if we look at this and factor out the voltage, the capacitance due to the capacitors in parallel is simply clearly them added together, right? They're added together. So capacities in parallel add directly. Capacitors in series add inversely. Now, what do I mean by parallel and series is very simple. If I have to go through one to go through the next to go to the next, they're in series, right? That's series. In parallel, well, if I have choices, I can go through this one to get to here, or I can go through this one to get to here, or I can go through this one to get to here, then they are in parallel. If I can go through these and not have to go through anything else, right, and go through this, not have to go through anything else, go through this, not have to go through anything else, and arrive from point A, right, down to point B, then these capacitors are in parallel. Finally, capacitors essentially store energy by storing charge. And if we look at the energy stored in a capacitor, there are several ways to express it. They all come down to the same thing. The energy stored in a capacitor is QV over 2, right? Charge times voltage divided by 2. Or you could rewrite that as CV squared over 2. Or you can write that as Q squared over 2C. This is like we wrote Ohm's law and energy in oh no, we haven't gotten there yet. My apologies. So this is just different ways because we're using Q equals CV, right? All we're doing here is taking, oh, Q is CV, and stick CV in for Q. That gives us CV squared. And all we do is we take V is Q over C, right? And stick that in, and that gives us Q squared over TC. So these are the different ways of expressing the energy stored in a capacitor. QV over 2, CV squared over 2, and Q squared over 2C, and all of these end up as joules. And that's it for chapter 19.